So today we're going to be doing the inverse functions of either equations or functions. Now, an inverse function is a way to change the perspective of an equation. In essence, we're going to be looking at it through the lens of a different variable. If we look at this equation is set up from the lens of the y. You plug in an x and you get something back for the y variable. So we're looking at it through the lens of the y given an x. Let's say we want to swap that. We could look at it through the x given a y. And so now there's two ways that traditionally this is taught. Way number one, we're going to call this method one, swap x and y and resolve. So method number one entails us to swap the two variables. We're inverting them. We're looking at them from the approach of the other one, which means that this is x and this is y. And we're going to resolve for y, which means we do a couple things. We subtract 3 and we divide by 2. So if I divide everything by 2, that's going to be half of x and 3/2 is equal to y. And this would be our answer. That's the first method. Now, that will help us understand a little bit about graphing, on why some graphing things are going on, but I like to keep things, in my opinion, traditional, or in my opinion, I guess, what would be the correct way to say this? I think it's more intuitive to do it through a different way. An inverse is swapping the perspective. So why not just leave the function as it is? So 2, solve for the other. So just leave the equation as it is. Y equals 2x plus 3, and solve for x. We're trying to swap our perspective, so why go through the trouble of making it look like we kept our perspective the same? Just go ahead and swap it, or just go ahead and solve for the other one. So y minus 3 is 2x, and if I divide that by 2, that's 1/2 of y minus 3/2 is equal to x. Either way, we see the relationship is set up exactly the same. It depends on your preference. I tend to prefer this method because I think it preserves the integrity of the process that we're doing, looking at it through the lens of the other variable. This may help you out with, like I said, function notation and the idea of when we go to graph it, the x and the y swap is a big thing. But let's do one more just to make sure we got the idea. So if we were to do this, and I'm going to solve this through the original lens, I'm going to solve for the other variable, which means that I'm literally going to say, I want to solve for x. So I'm going to do a couple steps. My first step is I'm going to go ahead and distribute so that I can start getting that x out of the way. So negative 12x minus 48 minus 1. We're going to combine some like terms. And now we're going to start moving. I'm going to add 49 to both sides. And I'm going to divide by negative 12. So that's negative 1/12 y minus 49 over 12. Boom. There you go. Now, if you swap the x and the y, you would have y equals negative 1/12 x minus 49/12. Again, you'll get the same thing. I tend to prefer this method just because it keeps the core process of what we're doing very obvious. And the same thing is going to go on with this. Now with function notation, the only difference is how we write it at the end. And now this is where the original method, where we swap x and y and resolve, is going to be a little easier to plug in. But again, bear with me. We're going to go ahead and resolve for the other variable, and at the very end, write it in the proper notation. So we know that this stands for y. So when we go to solve for x, and I subtract 30, and divide by 5, so 30 divided by 5 is going to give us a 6. We know that is our inverted equation, but what would it look like as a function? Well, the way we write an inverted function is f to the negative 1. This says inverse because quite literally that's in the inverse direction on a number line is negative 1. So we're saying it's not f of 1, it's not heading in the positive direction, this is heading in the other direction. It's 1/5 x minus 6. And so the way that we read this is this says to find the inverse of x, plug in an x, but really what you're doing is you're plugging in the inverse of x, which is y, and solve. And you get yourself a y. But actually what you're doing is getting the inverse of y, which you're getting an x. Again, I'm more of a fan of method 2, but either way works with you. So why don't you go ahead, give 7 a shot here and see if 7 is going to present you with any sort of problems. Okay, so we know that this would be a y, x squared plus 5. There's two things. I would subtract the 5, and I would take the square root. Now, that may seem like nothing big until we remember that when we take the square root of anything and we're doing it in a process, we have to take both the positive and the negative, which means that f negative 1 of x is not a function. You might ask, well, why is that? Well, if we remember, to have a function, when I plug in a value, I should only get one answer. Here, this is showing me that I'm going to get 2. So I know that if I were to try and say that f negative 1 of x is the positive or the negative y minus 5, that wouldn't be the whole thing. That would just be part of it. I could either choose the positive or the negative, but we'll talk about that in a later video. But right now that we've gotten the mechanics behind it done, let's go ahead and try some scenarios and see if we can interpret what the inverse function is telling us. So, the State Fair is selling tickets for $50 a person to walk in. The flyer you see also advertises that each ride is $5 to ride. So your first thought might be, wow, this is an expensive state fair. And you are correct. But we're going to talk about functions and inverses. Let's go ahead and set up a rule for cost as a function of the number of rides you interpret. And now, the way that we're going to kind of test this out is we're going to come up with a few scenarios. I'm going to say x and then f of x. Or if I plug in a number, I'm going to plug in, given the number of rides, so rides is a function of cost, or cost is a function of rides. So I know that when I plug in a ride, I will get a cost back. And we're going to start at 0 rides. You walk in, how much do you spend? Well, $50 to walk in. So you spent $50 to watch your friends have fun. Sounds like a delightful afternoon. But for each ride you ride, the cost goes up by $5. And so what we see here, if we remember our arithmetic sequences, is that we see a number going up by 5 each time. Which means that if we use our arithmetic formula, we know that a sub n is a sub 1 plus the difference times n minus 1. We know in this case the difference, what we're adding each time, is going to be 5. And I know the first number in the sequence, so a sub 1 is going to be 55. And that's all we'll need. So let's check out what we got. So a sub n is n minus 1, given the number of rides. A sub n is 55 plus 5n minus 5. So a sub n is 50 plus 5n. Or if I were to write that in a different way, I know cost as a function of rides is equal to 5 times the number of rides plus $50. How do we interpret this? This says, if you tell me how many rides you want, I'll tell you the cost. And this is our interpretation of that. If you tell me how many rides you want, I can tell you how much it'll cost. And so with the inverse, what we're going to do is we're going to swap them. I'm going to say, okay, I have cost 5r plus 50. I'm going to solve for the other variable, which means I'm going to subtract 50. So cost minus 50 equals 5r. Then I'm going to divide everything by 5. So 1/5 c, 50 divided by 5 is 10. Boom, we have that. And I'm going to rewrite that as, okay, cost, the inverse cost of the rides is equal to 1/5 r minus 10. So that's the inverse function. And how would we interpret this? Well, remember, we're talking about the other variables. So we're going to have to say, if you tell me the cost, or better yet, how much you want to spend, I can tell you how many rides you get. So this tells us literally the exact opposite. We say, hey, I want to spend no more than $75. You're like, okay, cool. I'll tell you how many rides you can get. So I'll plug in my 75. 1/5 of 75 is going to be 15. 15 minus 10 is going to be 5. You can ride 5 rides and stay within your budget. Perfect. So why don't you try number 11? Number 11's a little more enjoyable. Pause the video, give it a shot, and see how well you do. Okay. So at this point, Leo's jumping out of a plane to save Gemma from crashing without a parachute. So I don't know why Gemma would jump out of a plane without a parachute, but Leo's trying to save her. He goes to jump from an altitude of 5,000 meters. So what we've got is we have an altitude, and we have time that is passing. And we know when time is 0, we have an altitude of 5,000. And if we know that gravity, little g, is 9.8 meters per second squared, which means that each second we're going to square it and multiply it by that 9.8, and we'll get how far we've fallen. So after 1 second, what we're going to do is we've accelerated. Let's get this set up. So 1 second squared times 9.8 meters. We've fallen 9.8. So we're going to take 5,000 minus 9.8. Boom, we're going to round that to 4,990. We'll leave it in the calculator like that, but we're going to round it to 4,990. We know that at 2 seconds, we're going to take meters per second, so 9.8 times 2 seconds squared. We've fallen, at this point, 39.2 meters. So 5,000 minus the 39.2, and we get a height of 4,961. And we're going to do the same process each time. So seconds squared times 9.8. We've fallen 88.2. And we get 4,912. And so what we notice is, should have written this table the other way around, but the basic idea is that, albeit each time we're changing, let's see, 5,000 to 990, we went down by 10. 4,990 to that, we went down by, 29? And then again, from 4,961 to 4,912, we went down by 49. This isn't consistent, so we know it's not arithmetic, but if we take the second rate of change, so -10 to -29, we went down by 19, and here we went down by 20. Now realize, because we rounded, these should technically be the same thing. So we know with the second rate of change, that's going to be a quadratic function. That makes sense because we're squaring our time. So our original function is going to be our height as a function of time is 5,000 meters minus 9.8 t squared. Let's interpret. If you tell us how long since Leo jumped, we can tell you his altitude. Boom. And so there we go. Now, if we were to write an inverse rule, we would just swap those two values. We would say, okay, so h is 5,000 minus 9.8 t squared. Couple things going on here. We're going to subtract 5,000. Equals negative 9.8 t squared. We're going to divide by negative 9.8. So negative 1, 9.8 h. And does 5,000 divide by 9.8? No. Plus 5,000 divided by 9.8 equals t squared. I know these probably do reduce slightly, but we're going to go ahead and leave them here because the point is beside the algebra right here, and we're going to see what our interpretation is. So we're going to take the square root. So we're back at this thing where we have negative 1 over 9.8 h plus 5,000 divided by 9.8 is equal to t. So we have that. And now, unfortunately, what we're going to do is we can take either the positive or the negative answer. And let's take a look at the inverse and interpret which one we should take. So we know if you tell us how long since Leo jumped, we can tell you his altitude. So we're going to flip that. If you tell us his altitude, we can tell you how long it's been since Leo jumped. So if you tell us an altitude, whatever that may be, we can tell you the time. Now, Leo, when he jumped out of the plane, he was at 5,000 meters. 2 seconds before he jumped, let's assume the plane was on a flat flight, he was still at 5,000 meters. So what we notice is that, albeit this quadratic is a downward quadratic if we were to graph it, we know that part of that doesn't exist because at this point, scratch out all this, he was in the air and he didn't jump until this point where he started to fall. So when we invert this, we're going to invert this and we're only going to take the part of the quadratic that was, I believe in this case, going to be a positive number. Because we only have to deal with a positive time. So let's do that. So h negative 1 of t is equal to the positive square root negative 1 divided by 9.8. Again, now at this point, we're going to write t plus 5,000 divided by 9.8. And so that is how we got to our interpretation. if you tell us Leo's altitude, we can tell you how long it's been since he jumped. And there we go.